Okay, we're going to go through a more recent paper. This is March 2022. Just a few months ago, I realized we should get the new stuff out first, and then we can start going through the old things. Again, this is going to be a quick run through. I want to get this done as quickly as possible so I can get more stuff published. Let's have a look. So this is GES1 2022, a couple of months ago, 3 months ago. Let's run through it. Let's look at the first one. Okay, question 1 is really easy. Sample gas. A sample of exhaust gases analyzed by volume was found to be like all this much, like 2 parts sulfur, 4 parts oxygen. It's just a parts and ratio question, so it's really easy. Oh, they added like a little percent thing on the end. So was found to be 2 parts sulfur dioxide. Let's get sulfur, oxygen, water vapor, and then carbon dioxide. I guess I can write CO2. I guess I can write O2, SO2, sulfur dioxide. Don't need to write all those, but might as well. Nitrogen, I guess, is N2, but we can just leave it as N. I'm not sure about that. It doesn't really matter. We only care about the parts. Well, the first thing we need to do, well, let's just label all the parts. Let's get it all out of the question. So we've got 2 parts sulfur dioxide, 40 parts oxygen, 98 parts water, 198 parts carbon, and then 770 nitrogen. We need to add up all of these to see how many parts we have in total. So let me grab my calculator, and we're just going to add all these together. So 2 plus 40 plus 98 plus 198 plus 770. It's 1108. So I'm going to divide all of these by 1108. This is going to give me a proportion or a ratio. This is normally how all of them are. And then normally we would multiply this by 10 cubic meters or something, but they want it as a percentage. So we're going to convert each of these into a percentage in a second. In order to turn this into a percentage, when we multiply this, it will turn it into a decimal, and turn it into percentage, which is times by 100 at the end. I'm going to do that this bit for each one. I don't want to confuse it. So 1108. I suppose I could speed this up a little bit to not have to type it in every single time by putting it in brackets like this and times it by 100. So now we got, there's my percent. This is definitely a percent. It's 0.18%. 0.18% is definitely that. Right? Okay, good. Next one is going to be a 40. So I'm just going to go back here and change this into a 40 like that. Should speed things up a little bit. 3.61. And just do that for every single one. So it's easy. Huh. Look at my calculator. Bit glitchy, huh? 98. 8.84. Well, yeah, I think it is 8.84%. 198. Ah, it's glitchy. I have to keep doing that. That's weird. 198. Just put a 1 in there. 17.87. And then 770. Weird glitch. 770. Alright. And we got 69.49. 69.49%. Yep, we could times all these by hundreds, I suppose, just to show our working. And I could even put all this in brackets to be really clear about it. But there it is. Those are all percentages of all of the gases. On to the next question. Okay, this is question 2. I thought I'd blow it up so you can see it really clearly. I'm going to have to zoom out to fit this all on the screen, but it's just a bit of algebra. Let's write down the first one. Let's write down it as being 12ab cubed over 6bc divided by 2ab squared over c squared. Okay, I just wrote down the question to make sure I didn't copy it wrong, because it's quite easy to copy it wrong. Okay, and now we're gonna get to work on this thing. I could simplify a whole bunch of this stuff straight away, or I can do keep flip change on that divide, because anytime you got 2 fractions like that, we should be keep flip change. We can call that KFC, which is keep flip change. Easy to remember. So I could do that straight away and then simplify stuff, or I could simplify stuff straight away. It doesn't make any difference. I know quite a lot of you like to flip it without touching anything, so we're gonna do that first of all. Again, lots of different ways to do this. So c squared 2ab squared. Now let's see what I can cancel. Effectively, this is just one object. There's no need for this multiplication in the middle. I could have just written it all together. But let's see what we can cancel out. So this a and this a can be cancelled. This b cubed can go with this b1 and this b2 because they add up to b3. They add up to exactly the same amount. And then the c and the c squared can be cancelled. Oh, just before I do that, look at this 12 and the 6 and the 2. 6 times 2 is 12 and 12, so that cancels as well. Let's just rewrite that for what it's worth. It'll be c squared over c. So obviously it's just going to cancel down to be just c. So the answer is just c. That's it. Really easy for the first part. Let's see if we can get part 2 or part B up here. Let's have a look. B, I'll copy down carefully, hopefully no mistakes. 12ab cubed over 6abc times by 2ab squared over 12abc squared. Again, really easy because it's multiplied. It's even better. Don't even have to flip it or anything. Let's just see what we can cancel out straight away. This a can go. Oh, this a can go. And then let's see. I'm going to take this b and this b and this b squared and cancel all them out. And then anything else? I can't really see it anymore. It's getting a bit messy. Oh, let's take out those 12s. Okay, now I definitely can't see it. Let's rewrite it in neat. So just be careful not to miss anything. There's my b cubed. I've got this times by the 2. Nothing else. And on the bottom, I've got a 6 and there's a c. 6 and a c. And there's another c squared over here. I'm being really careful not to miss anything, because it's very easy to skip over those. Maybe I did skip something. Let's have a look. The 2 and the 6 can cancel down to just be a 3. That's really good. It'll be a 1 on top, but no need to write that. And I think that's it. I think we've got b cubed over 3, and the c and c squared can become a c cubed. Simplify each of the following expressions. Well, yeah, that's simpler. It's better. All right, on to the next one. Okay, question 3. There it is. You can see it nice and clear. Determine the equation that describes the plotted data. The data plotted. So they actually gave us a graph this time. Usually we have to draw it ourselves, which is nice. It saves a little bit of time. We just take the equation off it. The equation is y equals mx plus c. So let's get to work on that. It's going to be a quick, easy question. Y is equal to mx plus c. This will describe pretty much any straight line. Well, yeah, any straight line on a graph. And we can get the points off the graph. The c is the easiest to get because it's just there. C is the y-intercept. This c is a y-intercept. And you can see it's at 4. It touches a 4. So that immediately I can say it's equal to 4. Now to get the m, we need to look at m is equal to rise over run. So I can get that from my graph. Or it's all the same as also y2 minus y1 over x2 minus x1. We don't even need this. It's too complicated. We can just use rise over run from the graph. We want to pick 2 points that we can clearly see on the graph that clearly cross the background. This one doesn't. The 1 is no good. The 2 is good. Okay, so we're going to zoom in on this a little bit, I guess, to have a look at it. I'm looking for 2 points that clearly cross the background. Like I said, 1 is no good. And I can see that we go 2 across and we go like about 10 up. Sorry about the photo. It's a bit low quality. I know it's not usual PDF quality, but okay, it's the best I could do. We got a 2 on the ground, on the run, and going from 4 up until 10, that's a 6 on the rise. So we've got 6 over 2 as our rise over run, which simplifies down to 3. So I guess we should write that down over here. Let's keep it all together and I'll make it fit. There we go. That looks better. So this is going to be our 6 over 2, which is equal to 3. So the whole thing all together, which is the equation that they want, is going to be y is equal to 3x plus 4. This will describe that line. Great. Part B is determine the value of y when x is equal to 2.5. I might be able to get it off the graph, but it's a bit wonky. It's a bit small to see. So I'm just going to plug it into this one. It's really easy. So y is equal to 3 times by 2.5 and then plus 4. Grab my calculator, try that on there. 3 times by 2.5 and then add 4. 11.5. So 11.5. When x is equal to 2.5, y is equal to 11.5. Easy. Next one. Okay, so far this test has been really easy. The first 3 questions is really easy, which is actually really good because the first 3 questions you need to get 50% on the first section. And let's see, there's only like 1, 2, 3, 4, 5, and 6 on there. So we would have got a pass grade if we get all of those right. The rest of them are just bonus then. The next 3 questions are a bonus. And this is a really hard one. I don't expect many people to be able to do this. This kind of test, they have some really hard ones on there, just thrown in. Just for political reasons, just to say they cover it on the course, I suppose. But this is some really tricky stuff. Pythagoras' theorem is theorem, isn't it? Theorem? Not sure. It's yeah, okay. Pythagoras is pretty easy, but the way they set this up is really hard because we do not have all the information. So what we're gonna do is it's gonna take a little while to go through the whole thing, and we're gonna break it down to little sections. Let's see what we can do. The first thing we need to do is like basically draw this as 2 back-to-back triangles. Here's a blue one, and then let's get a red one on there. And this is going to be the key to it because they share the same backbone. Like these 2 triangles are back-to-back, so they have this line in common here. But everything else is just different. We're going to have to even use simultaneous equations to solve this. If your algebra is good, this won't be too bad. If your algebra is a bit shaky, then this is going to be pretty tough. Let's see. I'm going to drag my triangle off to the side so we can pull it apart and have a look at each part individually. Okay, so what do I know about this thing? Let's see if we can line it up. This side is root 13. The base is 2x. And this side is unknown. I'm going to call it y, just to call it something. Just so I can refer to it and say that y is equal to this side. Same thing on this side. This is also y. And you can see they're exactly the same. Again, that's the key to this. This is going to be square root of 10. And this is just x. Now we're going to run Pythagoras on both sides of this. I'm going to make it a little bit more space because it's going to be a little bit big. Okay, so you know Pythagoras is a squared plus b squared is equal to c squared, where c is the longer side. So I can take my 2 shorter sides. So I can rewrite this being 2x squared plus y squared is equal to the 13, root 13 whole thing squared, just to write it all out in full. Okay, this root 13 is really good. It's going to cancel out. It's really nice. I'm going to be left just with 13 because the square root and the square cancel. Y squared just stays as y. Now 2x squared is effectively saying 2x squared is the same as 2x multiplied by 2x. So be careful here because you have to multiply the numbers. The 2 times 2 is 4, but you also have to multiply the x. X times x is x squared. So this is going to be 4x squared. You have to multiply, let's just say that again, you have to multiply numbers by numbers and letters by letters. You just multiply everything by its like terms, you know? So like a's by a's, b's by b's, or x's by x's. Okay, so we get the x squared. So this side is pretty much done. There's a plus in the middle. We're almost good on this. I really want it to be equal to y squared, but I'll do that in a second. Let's do the other side then. So the same thing on the other side. We've got a squared plus b squared is equal to c squared. Wonderful. But now let's plug in the values for on this side. The a squared, we'll call that the base. We'll call that x. So it's just x squared. And then the other short side is y, the other leg. And then the longer side, the hypotenuse, is root 10 squared. Again, the root and the square cancel each other out. And we're left just with 10. And the y squared is just y squared. And x squared is just x squared. That's great. So now we're looking at this thing, and we've got these 2 equations. And the 2 things, well, the one thing they have in common is this y. So if I can transpose these to make y squared, or rearrange them, so we can do that with this one. We can say y squared is equal to 10 minus x squared. Oh yeah, by the way, this is the hard part. We're going to do some simultaneous equations on this. So this is where people start to drop it and lose it. If you can get this far, I'm sure you get some points. Okay. The good news about this is that this question is just the same every single time I've seen it. They never change the numbers. If you can just memorize this, then we're good to go. Okay. So let's see if we can rearrange this one. So we're going to have y squared is equal to 13 minus 4x squared. Can you see what I've done here? I've just rearranged it so I've got y squared on both sides. Let me just screw that down a bit. this y squared on both sides means that, because they're both equal to the same thing, it means that this must be equal to this. So I'm going to line it up like that. I'm going to write them side by side. So now we should be able to say that 13 minus 4x squared is equal to 10 minus x squared. This is because they have that common side. They have this 1 in the middle. That's the same thing, right? Okay, let's solve this then. We've got all these negatives. I'm going to add 4x squared to both sides. Adding 4x squared is going to turn this into a 3x squared, because 4x squared minus x squared is 3x squared. Then I'm going to minus 10 from both sides. So it's 13 minus 10 is going to give me 3. I'm sorry if I did that a bit quick. Might have been a bit quick, I suppose. Okay, then we're going to divide both sides by 3. We're going to get 1 is equal to x squared. And then we're going to square root both sides. The square root of 1, let's just square root like this. The square root of 1 is just 1. And this is x. It's actually technically plus and minus 1, but we can't have negative distances. It wouldn't make any sense in our diagram to have negative distances, so we keep the positive version only. So I can just say it's equal to 1. X equal to 1. Wow, that was exciting, right? Okay, so let's go up and plug it back in and see what we can do. So we got our diagram up here. We're trying to find y. It says determine, using the theorem, with a U, I suppose, determine the length of AC, which is this height in the middle. AC is the height of the mast in the center, right? Or the height of the triangle. So we can just plug it into one of these. Now we've got x is equal to 1. We know, we just need to find out what y is. And I've got loads of equations here. Tell me what y is. Again, I can just run Pythagoras on it one more time. But I can literally just take it from here. From this one, it's just fine. So if x is equal to 1, I can say y squared is equal to 10 minus 1. Right? Because x is equal to 1. I should write that over here. So x is equal to 1. Even if x was equal to negative 1, it wouldn't make any difference. Because you square it, it becomes positive. Okay. So now we've got x equal to 1, y squared is equal to 10 minus 1. You can see where this is going. Y squared is equal to 9. Square root both sides, we get y is equal to just 3. Again, it should be plus and minus 3, but we can't have negative distances when we're talking about distances, triangles. So it's just positive 3. So the height of the AC is 3. It's all in centimeters, so I guess the answer will be 3 centimeters tall. Again, they just really just have exactly the same kind of question each time. So run that through a few times, memorize the technique. This is the tricky bit, the simultaneous bit at the end. You run them side by side and we can line them up. Next question. Okay, question number 5. Is this one again. I'm sure we've gone over this in another video and another test recently. This one is coming up more and more often. I'm seeing in the newer papers, the 2022s, that's why we're going over them. They're heavier on the pure mathematics side, which I understand is more difficult for you guys, being engineers. But again, these are just set questions. You can just memorize the technique. This is actually a really easy one, even though it looks diabolically hard. The trick to see is that we can cut this into a square in the center. This is actually a perfect square because the radius is r, and this is 2 radii. It's going from one side to the other side. So you can see if I put like a little line in the middle, this will be an r, this will be an r. And you can also see that this would also have to be r here, and this would also have to be an r here. So this is also 2r along the base and 2r along the height. Then what we're going to do is calculate the area of this whole square and then just basically subtract a circle. You can see it's 2 halves of a circle from that. I need to explain my rationale as of doing that. So I'm going to draw some diagram to explain it. I'm going to say that here's my original shape. I'm going to copy theirs. I'm going to use actual circles in it. Not that I really need to. I could just do it by hand. It's just a sketch to explain my rationale, like I said, my logic. So first thing I can do is I can say, well, I can actually cross out all these lines. We don't even care about this. It's kind of like a red herring to be looking at that. What we want to be looking at is the center section here. And like I said, we've got 2r on the base. We've got 2r on the height. Let me clean this up a bit. 2r on the height. I don't need this. And we want to take this as a square. So I'll just draw that as a square, which is 2r by 2r. Whoops, 2r by 2r, and then we're going to subtract literally one circle from the center of it because it's 2 halves of a circle. So here's a circle, and the radius of this is r. And I suppose I could say this shaded area is equal to a square minus a circle. This is my explanation, my rationale. Now we're just going to run through the actual calculations of this. Obviously the area of a square is base times by height, so it's 2r multiplied by 2r. And then let's move it down so you can see it a bit better. And then the area of a circle is pi r squared. So that's all we need to do. We're just going to minus these guys off from each other. Again, when you multiply 2r by 2r, you're going to multiply the numbers by the numbers. So that's 4. Multiply the letters by the letters. That will make the r squared. Minus, well, pi r squared. Nothing more to do on that. Now we have to make it look like they have it. So they have it saying 4 minus pi and this whole thing in brackets with r squared on the outside. So it's a bit of a clue what to do next. Basically, I'm done, but you know they want to make me to actually make it look like this. So you can see that they both have r squared in common. So we're going to pull this out as a common factor. Again, this is a little bit difficult for you guys pulling out common factors. This is factorizing, but hey, it's what we need to do to make this thing fit. That's it. You can see what I've done is I've basically divided out that r. I pulled it out. A bit like dehydrating vegetables, I suppose. You got like a carrot and then like some onions, and you pull out the water from it, and you're left with just this. And then you put it back in again, and we should get back to what we had originally. If you multiply back in that r squared, it goes back into being what we had originally. So you can tell it's correct. I can go forwards and backwards. 4 minus pi r squared. You could also tell it's correct because they gave us the answer. They gave us what to hit what we're heading for. That's it. Done. That's the whole question. 8 points. Really, really worth doing. Next one. Okay, this is number 6. Number 6 is really hard, diabolically hard. Like so hard I wouldn't even bother doing it. For 10 points, you've already got a pass grade if you've done the rest of it. You do not need to do this. It's just overly complicated, ridiculously complicated. You got 1,000 ice cubes, you put it in an empty cylindrical container with a hemispherical base, and the ice cubes have this dimension, and then the container has a certain dimension. And then the ice cubes are going to melt. And the problem with ice cubes melting is that obviously, you know, ice has a greater volume than water. That's why ice floats, you know. So we're going to have to do a lot of work on this. We're going to calculate the volume of the ice. We're going to melt it, and we're going to pour it into the container and see how deep it is after that. So first of all, let's get 1,000 ice cubes. Let's see. The ice cubes are 2 centimeters by 2 centimeters by 2 centimeters. So I think I got one somewhere. Let me just go grab an ice cube. All right, there's my ice cube, and it is 2 centimeters by 2 centimeters by 2 centimeters. All right, and there's 1,000 of them, so obviously we can go for volume of that. So let's make some space. We're gonna need the volume of the ice cubes, of 1,000 ice cubes, of 1,000 ice cubes. So the volume of one ice cube, the volume is going to be base times by height times by length, which in this case is just 2 times by 2 times by 2, which is equal to 8 centimeters cubed. Of course, we've got 1,000 of them, so 1,000 times by 8 is going to give us 8,000 centimeters cubed. This is 8 liters, which is fantastic. Okay, this is the ice as it's frozen. Then we're going to melt the ice. Well, we're not going to melt it just yet, actually. I got to take this volume, and I got to work out how much it weighs, because that weight will not change between the weight of the ice and the mass of the ice and mass of the water. But what will change is the volume. This volume, we're going to see how much it weighs. Or well, the mass is. I should say mass rather than weight, or whatever. So we've got the density. They said take the density of ice is this much. Meters cubed. So kilograms per meters cubed. I suppose I should convert this into meters cubed. This is equal to 8 liters. So there's 1,000 liters in a meter cubed. So let's just get 8 and divide it by 1,000. And it comes out to be, well, yeah, great. This is the same as 0.008 meters cubed. If it has a little -3, it means there's 3 zeros in front of it. I'm going to do it like this because it's easy for me to type on my calculator just for a short number like that. If it was a bigger number, okay, fair enough. So this is how many meters cubed we got. Now we want the mass of the ice, the weight of it, right? So they gave me the density. So density is equal to mass over volume. So I have to think about that every time I do it because I'm thinking about like something like polystyrene or styrofoam, something that's like really, really light. It has very little mass, but it has a big volume and it has a low density. So I can think of that in terms of numbers, like 1 divided by 10 is 0.1. Okay, so I've got the density. They gave it to me. They said it's 912. And I don't know the mass, that's what I'm trying to calculate. And I do know the volume, 0.08. So I can multiply these guys together to get my mass. So let's multiply this by the 912 to get 7.296. Mass, or X, 7.296 kg. Let's just check that. Yeah, okay. This is the weight, this is the mass. I keep saying weight. It's the mass of the ice cubes. Great. So this is what's going to be transferred into water, right? We're going to melt this thing down into water. And now I want to know how much volume this thing takes up. Pure water is just a one-to-one relationship. So like 1 kilogram is going to be 1,000 milliliters, or it's a 1 liter. So okay, I'll explain that a little bit better. They do say the density of water is 1,000 kilograms per meter cubed. It's because we're talking about fresh water, obviously, because salty water is difficult to freeze. It doesn't freeze actually. It has to be pure water because it doesn't have one freezing point. Oh, it doesn't matter. It could be frozen and it doesn't tell you the temperature. Anyway, getting ahead of myself. Let's have a look at the next one then. So what we're going to do now, volume of the water. Okay, so volume of the water. We've got this mass. We've got the density. Let's get the density equation. We've got density is equal to mass over volume. I'm calculating for volume this time. I know my density is equal to 1,000 kg per meter cubed. I can just pop this out actually, looking at it, because like I said, I know this must be 7.296 liters, which is really good. I guess I want the volume in. What I want the volume in? What are we working in for the actual cylinder, the actual shape, the actual object? The object is in centimeters. I want it to be in centimeters because I want to get the volume in centimeters. So I'm going to go this way. I'm not going to use this density equation. I'm going to go straight from this many liters into times it by 1,000 to get 7,296 centimeters cubed. Because I want my work to be in centimeters cubed, not in meters. This calculation will give it to me in meters, and it's a bit difficult to convert it into centimeters cubed. This is a little bit easier, a little backdoor. Okay. So I got this much water. So let's just make this clear. Let's get rid of all this. Let's just say volume of water is this much. Great. This is what we're going to be now filling the container. So let's take a look at the container. In the question it says, we're going to move this across so we can see it. I think, yeah, we're going to scoot it across a little bit because we're going to need it over here to draw the thing. Let's move it across. Okay, so we're going to draw the container. A hemispherical base. It's a cylindrical container with a hemispherical base, which basically means it's like an upside down gas tank with a bulbous top. So this will be the cylinder. It'll look a bit like this, and then it has a cylindrical base on it, so a hemispherical base like this on it. So we don't know the height of it. We don't even need the height of the thing. It can be infinitely tall. We're not going to fill it to the top. We're just going to fill it full of water. This base is going to be completely full, and then the remaining of the water will be left up top. Will be pushed up to the top here. So we need some information about this thing. I'm going to make it a little bit smaller. It's a little bit big. Can't fit the rest of my work on that. Let's scoot that down. Move it across. Okay, great. We know the volume of water is 729.6. 7,296 centimeters cubed of water. What are the dimensions of this cylinder? I don't know how deep it is. I know its radius. The only thing I know about is radius. It has an internal diameter of 28 centimeters. 28 centimeters is across. I'm going to convert this into radius. I know you guys go straight from diameters into volumes, but that's absolutely fine. I need, but I'm going to turn it into radius. The radius, therefore, is 14 centimeters divided by 2. I need the volume of this hemisphere first. I guess we're going to work on the hemisphere. Let's have a look at the hemisphere. The volume of a hemisphere is going to be the same as a sphere, which is 4 over 3 pi r cubed. And then we could divide the whole thing by 2. This will be the volume. Right? It's the same as a sphere, 4 over 3 pi r cubed, and divide the whole thing by 2. I know the radius is 14, so we're good to go on this. I can just type it through my calculator. I could simplify this. I'm just not going to bother. Why? Why would I? I can just crunch it through my calculator, divide the whole thing by 2. Just got to be careful how I do that. So grab my calculator. Let's see. We're going to do 4 over 3 first of all. 4 divided by 3. Great. Times that by pi. Okay. Times that by 14 cubed. It's only going to cube the 14 because it's only touching that, not the whole thing. Okay. Divide the whole thing by 2. All right. So we've got this many centimeters cubed in the hemisphere top. The 5747.02. 0.02 centimeters cubed. This is now the whole hemisphere, right? It's filling up the whole of this cap. And whatever is left over between this, which is the water, and the hemisphere will be filling up the cylinder part. So let's look at the volume of water in the cylinder. Water in cylinder. So we're going to take the 7296 minus this number, the 5747.02, because we have filled up this whole top. And what is left over will go in the top. We'll go in the cylinder. 7296 minus the answer, we get 1548. 1548.98. I'll call it. I'll round that 7 up to an 8. Okay, centimeters cubed. Fantastic. And then how deep will this be in the cylinder? So we're going to fill up the cylinder. The only thing we know about the cylinder is its radius, because we know its cross section. From the radius we can get the cross section, and then we can get the height from this. So let's look at the depth of the water. Depth of the water in the cylinder. And we're going to use the volume of a cylinder. The volume of a cylinder is base times by height. The base is a circle, so pi r squared, and the height we don't know. We're calculating this. The radius we do know. The radius is 14, so pi 14 squared times by h, and we do know the actual volume. The actual volume, the cubic centimeters we have to spend is this much, so we can say 1548.98, and we're going to solve this. Let's scoot it down a bit so we can get to work on it. Okay, we need to transpose this a little bit and get h by itself. So actually we can just divide through by all this chunk. So we can say 1548.98 divided by pi and 14 squared. I have to be really careful how to put this in my calculator because it will mess it up if I don't put all this in brackets, for example. But you'll see me do it. So we got the number already. We divide that by, in brackets, the pi, times that by 14 squared, and then close brackets. That's it. 2.51. 2.5156, I suppose, centimeters deep. So it's going to be that deep in the cylinder. We're not quite done yet. We're almost there. 2.51 is this much. Let's go back to my picture. 2.5156 is this much deep. But I'm pretty sure in the question they're asking for, calculate the maximum depth of water remaining after the ice is melted. This is going to be the full depth, right from the bottom of the tank, right from down here all the way up to here. So it's going to be the depth of the radius of that cylinder as well, that hemisphere top, because it's going to be a radius deep, right? It's going to be one radius down. We already know the radius is 14, so I just need to add a 14 onto this. So this distance here is 14 centimeters plus the 2. This will be our final answer. So we can say the final depth is going to be 14, that's the radius, plus the 2.5156. That'll probably give us like 16.5156 centimeters deep. Ooh, and we finished that question. That's one of the most hardest questions I've ever seen on this Tyler test. It's so annoying having to go from ice into water. Really, really difficult. I wouldn't even bother doing it. I wouldn't bother the whole thing. It's a bit of a honey trap. It's a bit of a time-consuming, waste of time kind of question that will suck you in, that you think, oh, I can just solve it. We're giving me a bit more time. And really, you should move on to the next section straight away, which is what we're going to do now. Okay, we're going to start with section B. And, well, yeah, let's just start with section B. So, let's give it a go. A pump is uniformly accelerated from 500 revs per minute to 700 revs per minute in 10 seconds. Okay, so this is a spinning thing. It's a revolutionary question. It's about revolutionary spinning objects, right? And we should be using suvats to do this, and we should be using like angular suvats, but I'm not going to bother. I'm just going to use regular linear suvats because it just makes everything a lot easier. You don't have to remember two sets of notation, two sets of equations, which are essentially the same equations. They're exactly the same equations. But when you do it on a course, they might say that a little bit different on the course. So just bear that in mind as we go through this. I'm trying to simplify this. I'm trying to cut this down and make it work and conceptualize it in such a way that it makes sense in your head without having to remember too much information, because we're doing so much stuff to get through the whole. Most of my students, they do GES1 and GES2 together, and it's a lot of formulas to remember. So the less formulas you have to remember, the better. So let's have a look at this thing. I'm going to need a bit more space, I suppose. A pump is uniformly accelerated from, let's get rid of this. A pump is uniformly accelerated from 500 revs per minute to 700 revs per minute in 10 seconds. So we're going to start with this. We're going to start with 500 revolutions. This is 500 revolutions per minute. The reason why we're going to start here is because I want to do a suvat, the angular acceleration. So let's write down the suvat, S-U-V-A-T. Like I said, this is linear, but I'm doing it for the angular, but it should be fine. It doesn't make any difference. The only difference is on the suvat is in radians per second, and I've got this in revolutions per minute. I could write this down, my initial velocity. This is my initial velocity here, and this will be my final velocity, because this is what we're talking about. It's spinning around, and it's getting faster, right? We're going to get faster as we spin around. But it's in the wrong units. It's in revolutions and minutes, and I want it to be in radians and seconds. So that's the first thing we're going to do is fix these up so they are now in radians and seconds. So let's convert these into radians and seconds. Let's write it like revolutions over 1 minute. The first bit, this will be actually IU. So minutes is quite easy because we can turn it into seconds just by converting it by multiplying it by 60, right? So that's definitely 60 seconds. But how many radians are there in 500 revolutions? Well, a whole revolution is a whole circle, and if you remember, there's 2 pi radians in that, so we can multiply this whole thing by 2 pi, and it should pop it into the radians for us. Now I can do it on a calculator, and I can get my calculator and do 500 times by 2 pi. I got a couple of choices now. I can write it down as 1000 pi, or I can actually write it down as a decimal. Let's actually use a decimal. It's 3141, or yeah, 0.59. This is in 60 seconds, and I want it per 1 second. So what I'm going to do is I'm going to divide the tops by 60, and also divide the bottom by 60. Okay, it's a little bit complicated to say it that way, but it's really easy calculation. I'm basically just doing this calculation. I'm doing 314, because I got too many seconds. It's in 60 seconds. We want it in just 1, so let's divide it by 60. Okay, so now we've got 52. 52.35. This should be 99. This should be the now radians, because we converted the revolutions into radians. This is rads here, rads, and this is per 1 second. So that's really good. Let me move my suvat. It's just in the way. This is going to be rads over 1 second. We don't need to write the 1 second because it's just rads per sec now, which is what we needed. This is good. It's the right kind of units. Let's do the same thing for V. V is going to be exactly the same process. It's going to be 700. We're starting off 700 revolutions per 1 minute, and we're going to swap this out into being 700 revolutions per 60 seconds. Of course, we're going to turn the revolutions, we're going to multiply it by, we're going to multiply the revolutions by 2 pi, because that's how many radians there are in a full revolution. So 2 pi times by the 700 to get it into 0.229. Can't round it after that. Oh, okay, I'll do. This is radians. This is right, rads. In 60 seconds. That's great. And then we can divide by 60 again to turn that into 1 second, because this is how many radians we do in 60 seconds, and we just want in 1, so we divide by 60. So now it's 73.3. 73.3 is a nice round. Let's I don't know. 73.3. Let's keep it kind of like the same. Not that it makes much difference. It'd be 0.038. It's too many numbers, but okay, that'll do. This is radians per second, which is really cool, because now we got our starting amount. We got our final and initial and final velocities. We need this in order to do. We need this in order to do our SUVAT. So let's have a look at that SUVAT again. SUVAT. The initial velocity is going to be this number here. Is this made radians per second? We want it in radians per second because it says it there. Okay, got this one. I know I said that about 15 times. So my final velocity is this one here. Okay, great. And then what else do we know about it? Oh, it's in 10 seconds. 10 seconds. We need some SUVAT equations on this. So let me grab some SUVAT equations. S is equal to U plus V over 2 times by T, I think. And then also S is equal to UT plus half AT squared. And then one more, which is VUAT, V plus U. V is equal to U plus AT. And we're trying to find acceleration, which is fine. Angular acceleration, it'll be exactly the same as this, just different symbols. Angular acceleration, and we don't have our S, so we have to use a VUAT. So we can say, we're going to use this one right here. So we can say 73.3038 is equal to the initial, which is 52.3599 plus 10 times by A, because the T is 10 and the A is what we're looking for. We can subtract this and then divide by 10. So effectively we're going to have this number minus the 52 and then divide it by 10 at the end. And this should give us the A. So let's get that on a calculator. Let's see what happens. I've already got my 73 in there. We can type in the minus the 52.3599 and then divide the whole thing by 10. 2.09. So A is equal to 2.094. Now, normally this is in meters per second because we're talking about acceleration, linear acceleration, but we're not. We're talking about radians per second squared. So this will be radians, rads, or rad per second squared. That will be the final answer for part A. Great. That was part A. Oh, the whole thing was part A, really. Let's see what else we got then. I'll zoom out a bit so we can see it. The whole thing was part A. The number of revolutions turned during the acceleration period. Well, number of revolutions, this is the S actually of our SUVAT equation. The problem is our SUVAT is in rads, so I need to redo the SUVAT. So let's redo the SUVAT. How can we make it clearer? I'm going to do it down here because I'm going to need my information from here, in fact, to redo my SUVAT. SUVAT. I'm trying to solve for S. I've got my equations just up here. Here they are. You can see them. Okay. Trying to solve for S. I've got my time to be 10 seconds. I've got number of revolutions. They gave me revolutions. Wait a second. They gave me revolutions. The revolutions was 500 revolutions per minute. My final revolutions was 700 revolutions per minute. My final velocity was 700 revolutions per minute. Now the only problem with this is that and this is per minute. This is revs per minute. This is also revs per minute, but this time is in seconds, but we can convert 10 seconds into minutes. Again, this is not the only way to do it. It's just a nice, quick way to do it, seeing as it's lined up this way. Now, 10 seconds in 60 seconds, because that's how many seconds are in a minute, is going to be the same as 1/6 of a minute. I know that's weird. These are strange units, but let's just roll with it. We're going to use the VUAT or SUVAT, one of these SUVAT. I think this one's great. It doesn't have the acceleration in it. Yeah, that's the one. Let's use that. So we're looking for S. We take the initial velocity, which is 500, the final velocity, which is 700, divided by 2, and then we times by the time, and this is 1/6 of a minute. Like this. We just multiplied it by the T. This should work. Let's give it a go. And grab my calculator. We're going to be doing 500 plus 700. And I should put this in brackets, or I hit equals now. and then divide that by 2. Otherwise, it will only divide the last thing you typed in by 2. And then times this by 1/6. And it's going to come out as exactly 100. So it's exactly 100 revolutions. Remember, we're working in revolutions on this part of the question. So the answer is it does 100 revolutions in the acceleration period. Great. Next one. Okay, question number 8. Let's see what's going on here. We got a velocity of 70 kilograms is accelerated from stationary to a final velocity, and then decelerated again and comes to a stop. So it's a nice easy question because it's on a flat surface. It's not going up or down or anything, but it is in 2 stages. We're going to be doing one process and then another process. So let's do the first bit first, which is probably what the first part of the question is all about. Anyway, let's draw a quick diagram. We've got 70 kilograms. And it looks like it's going to be a whole suvat. So we've got SUVAT. Oh, I might be wrong about that because reading the question it says the accelerating force required. It looks like we might have an F equals MA on this. I'm going to have to use F is equal to MA to find that accelerating force. But in order to get the acceleration, I think I go to a suvat first and then plug it into this. So let's see which of those makes sense. We got 70 kilogram force mass is uniformly increased from stationary, so its starting velocity is 0. Its final velocity is 3.8 meters per second, and it's doing it in 10 seconds. So this is great. This is a suvat. We can use our suvat equations that we had a second ago. I'll write them out again. S is equal to U plus V over 2 times by T. And then S is equal to UT plus half AT squared. And then also it was VUAT, V plus is equal to U plus AT. Okay. We want acceleration, we don't have the distance, so we're going to use the VUAT on this one. Really good. So we can say the 3.8 is equal, that's the final velocity, 3.8 is equal to 0 plus the acceleration, which is what we're calculating. I could call this x, but let's just leave it as a, why not? Times by t, which is 10. Okay, so we've got 10t, so obviously the 0 doesn't do anything, 10a, sorry. We are going to divide through by 10. So we have 3.8 over 10 is equal to a, which is only equal to 0.38 meters per second squared. Meters per second squared, so like this. Okay, great. We're going to plug that equal into F equals ma in order to get the accelerating force required. This is the acceleration, and we're going to calculate the accelerating force required. Let me just double check that, because that number seems a bit small. Let's just see if it's all right. From stationary, yeah, to 3.8, in 10 seconds, okay. And we used the VUAT, so we got the final velocity is this, the initial velocity. Okay, good. That seems, it's really simple calculation. Just seems a bit easy. F equals ma then, to calculate this last little bit for the accelerating force required. We know the mass is 70 kilograms, so let's move that up so you can see it. We know the acceleration is 0.38, so from this we can get the force. So we're going to have 70 times by 0.38. 26.6. The force is 26.6 newtons to push it to get it up to that speed. That's what they're asking for when it says the accelerating force required. Great. Got it. So that's part A. The time taken in the deceleration phase. So this is a completely different question. So we're going to take it as a completely new part of the question. Let me just move my diagram across. And now we're talking about a new suvat, I suppose. Let's have a look. The time taken, so we're doing part B. The deceleration phase. So we got a new suvat, yeah. S, U, V, A, and T. And then it's decelerated. They gave us a deceleration. That's nice. So we're going to use this as negative 0.3 because it's slowing down. And then it's coming to a stop. So the final velocity will be equal to 0. Its initial velocity was the final velocity of the previous part, right? Because the whole thing was moving at this speed, at this velocity. So we can take the final velocity as being 3.8. And then we have to calculate the total distance traveled, that's in both sections. and the time taken. So I want the time taken for this part. So let's calculate the time taken. We're going to be using our same Suvat equations as we had a second ago. I can just go grab those. Let's move them across here. Fantastic. And then we don't want anything with s, so we're going to use a vuat again, this last one here. So 0 is equal to u, which is 3.8 plus, well, negative 0.3 times by the time. Easy. Really good. Okay, so then this is a negative, so we can pop it over to the other side. So we could say like this. We could say 0.3t is equal to 3.8, and we divide both sides by 0.3, so we get t is equal to 3.8 divided by 0.3, which is 3.8 divided by 0.3 is equal to 12.6666, 12.6 recurring. That's what that means recurring on my calculator. This little bracket thing, I can press this button to get like this. So 66667, it's just going to round up at some point seconds. So this is the time taken in the deceleration phase. The total distance traveled. Well, the total distance traveled is in both the sections. It's both in the acceleration and the deceleration. So I need the total distance traveled. I need s in the deceleration phase. We'll do that bit first because we're right here. Let's go do it. And then we'll do the total distance, the distance for the acceleration phase, the first part. Let's see if I can fit it on a little bit better. Okay, so what's the distance traveled? Do I trust my numbers? I suppose I could. I can just use this one up here then. Oh, either way, all my equations for Suvat. There's meant to be more. There's 5 equations for Suvat, but I'm only using 3 because I don't want to remember more than this. I can rearrange them to get the other ones, I think. And this is enough to get us through GES1 for sure. Okay, I'm going to use the top one here. So this is part C. So it's in 2 parts. This is a deceleration phase. I should write that out, but I'm not going to bother. So the s is equal to the initial velocity, which is 3.8, the final velocity, which is 0, everything divided by 2, times by the time taken, which is 12.6667. This is the first part. Well, that's actually the deceleration. So I can calculate this. Oh, we might as well do it. We're here. 3.8 divided by 2 times by 12.6666. I got 24.0666. 24.066667 meters. This is only in half of it, right? Now we have to go back to the original, which is over here, and find how far were we traveling here. Does it tell me any more information? I don't know. Don't think so. Can we use the same equation? Can we use the initial plus final? Yeah, we can. Let's use s is equal to the initial plus final divided by 2 times by the time. Okay, so 3.8 plus 0, which is just 3.8, divided by 2 equals times by 10 equals 19. So it's 19 meters in the first bit. Let's add both those together. Let's just add the 19 on here. Let's try to make it look like it made more sense, but let's just add 19 onto this one. So now I can take my 24.0666 and add 19. We get a final distance that's 43. The total is going to be 43.067 meters. That would do. Is the total distance traveled in both sections when you add them together. Very good. Next question. Okay, let's do question number 9. This is, it used to be quite difficult. It used to be a really long calculation. This is a sideways, like jib crane basically, or it's a mast is suspended by 2 chains, like loading a ship or from one ship to another, determine the tensile forces. And I used to have a very, very long method for calculating this, but someone showed me a very nice method. One of my students showed me a very nice method, a much quicker method of calculating it. So we're going to try to do it that way. See if I can remember how to do it. It's very quick, very, very easy to get the 8 marks. We don't have to go through a very long calculation with lots and lots of parts. Okay, first thing we're going to do is draw a picture of the diagram, I suppose. I really want these measurements. I really want the angle of this triangle here. So that's what we're going to calculate. We've got 6.8 and 5.1, and we got a right angle here. Let's just pick the smallest angle because it's a nice clear one to see. So we'll start with this. It's a right angle, so we're going to use SOHCAHTOA. I'm just going to draw a little guy here. This will be the opposite, this will be the adjacent, and this will be the hypotenuse, just so we're clear about that. So it looks like I'm going to use SOHCAHTOA on it. So here's SOHCAHTOA. See the old Harry called a lot of haddock trawling off Africa. Okay, and we're going to use adjacent and opposite. Adjacent and opposite is a TOA. So we can say tan of the angle is equal to the opposite over adjacent. Let's just write that out first of all. And then we can say the angle, we don't know what it is, we're trying to calculate it. Opposite is 5.1 over 6.8. And then we apply tan -1. So I could have done that to start with, but I thought I'd write it out. Looks like this. Okay, and this should give us the angle, right? So let's grab a calculator and try the angle on that. So 5.1 divided by 6.8 is just 3/4. That's nice. Okay, tan -1 is shift tan, and it gives me tan -1. This is to get the angle out of it. Put it all in brackets, make it look good. 36.869. So the angle is 36.869. 89. Oh, it's really bad on the rounding. So let's just round it up to 87. So now this angle here is 36.87. We can grab the other angle by doing 90 minus it. It's because all the angles inside of a triangle add up to 180, and we've already got 90 used. So what's left over is 90. These two must add up to 90. So 90 minus that one gives me the 53. I'm sure you can work that out. I did that a bit quick. Was it 53.13? 53.13. Great. So this is the other angle. So now we're going to get to work on this. Let me just scoot all this off this one side. I don't need all these calculations to do with the angles anymore. So I'll pop them down there. What I do need is this triangle again. We're going to turn this into a forced triangle rather than a distance triangle. So right now it's a distance triangle. And this is the magic part. This is the really cool part. This thing is lifting 150 kilograms. So we have to take 150. Oh, I'm just trying to make it all fit. So sorry about this. Let's make it look nice. Let's drop these calculations down here. Yeah, doesn't really do very much. So 150 kilograms is pulling straight down. So the amount of force it's actually lifting is on the vertical here. Can I remember how to do this? I think I got to draw a triangle like this. And it has to be a right angle. So how's that going to look like a right angle? And it has to be parallel to it. Oh, this one. I normally draw on the small side, actually. That's right. So this is the small side. This is the big side. I'm going to draw a triangle that uses, there we go. It uses this one as a right angle. I think that's right. This is 5.1 on the distance. But the point is that this should be parallel to this. It doesn't quite look like it is in my picture. And we're going to calculate the force on this side because this is the tension. We've been asked to find the tension in BC. We're going to find the tension here. And then we are also going to calculate the tension on this bit, which will be equal to the tension on this. Somehow, some way that this tension will be the same as this one. It just is. It just works. And it's really, really nice. Much quicker formula than anything else I've seen before. So we know the angles, right? We know the angles. There's this small angle. The thing about this is it's made from a bunch of small triangles. These small triangles are all the same as the big triangle we had over here. So this is 36.87 degrees. So I can say that looking at this triangle here, I can say this angle down here must also be 36.87. And you really have to kind of get involved as a human and say, I think this is true, and just make it true, and everything else will follow afterwards. That's the problem with physics, or that's what physics is about, is getting involved. You can't just trust the calculations. You have to change things from positives to negatives and set things up in the correct kind of way. So basically I'm working with this triangle. I'll pull it out so you can see it. It looks like this blue triangle. This is the force triangle. Now this force triangle is lifting that 150 kilograms. So I didn't do the calculation on that. We've got 150 kilograms, which is under gravity at 9.81. So it'll give me a force of 1471. 1471.5 newtons. This is on this side, which it looks like is the hypotenuse. We know the angle is 36.87. Let me label up my sides now. Draw a little guy down here. This will be my opposite. This will be my adjacent. Now these are the two sides we want. The adjacent is the BC, and the opposite will represent the AC, and it'll just work. So I know that my hypotenuse is the 14.71. My bad. 1471.5. Yes. So I want the adjacent. Let's go for the adjacent first. Adjacent and hypotenuse. Adjacent and hypotenuse is the K. So let's do that. This will be tension. Let's write it out. Tension in BC. Yeah. It's going to be using the K. So we can use cosine of the angle is equal to the adjacent, because this is the adjacent, over the hypotenuse. Cosine of the angle is 36.87. The adjacent, we'll call it x, over the hypotenuse, which is 1471.5. You can see how easy this is going to be. I just multiply it up. So we're going to get 1471.5 times by cosine of 36.87. This will be equal to x, which is the tension. Let's see if we can make that work. We've already got the number in the calculator. Just times that by cosine 36.87, close brackets. It's equal to 1177.198. That would do newtons. This is the tension in BC. Now we're going to do the same thing. We're going to solve for the tension in AC, but it's given by the opposite side. This tension in A to C, this one is given by this one. I mean, they're parallel to each other, but they actually show the same forces, which I think is crazy. Tension AC. And as we're looking for the opposite, we got the hypotenuse. We're going to use the SO. From SOHCAHTOA, we're going to use the sine. So we can say this is going to be equal to sine of the angle is equal to the opposite over hypotenuse. Let's make a bit more space so you can see this clearly. I'll put it up here. Okay, it's looking good. So now we can say sine of, we know the angle, it's 36. It's 36.87. We know that we don't know the opposite. We'll call it y. And then we don't know that we do know the hypotenuse. It's this 1471.5. We multiply that back to the other side. Like this. Oh my goodness. Sine 36.87. Now this is equal to y. Right. Let's give it a go. So 1471.5 sine 36.87. Close that up. We got 882.9. 882.9 newtons. This is the tension in AC, and this is the tension in BC. So I expect the tension in BC to be higher because it's doing more work. It's closer to the load, so it's lifting it more. And the tension in AC is less because it's further away. So it actually makes sense, and it looks really good. That's it. This is the quick way. There's another way which is much longer, which involves a lot more calculations, but this is so nice. Let's go for the next one. Okay, let's do number 10. Almost at the end of this test. 10, 11, 12 to go. A packing crate, a packing case with a mass of 50 kg has a force applied to it which causes acceleration on a horizontal plane, and the force is applied at an angle at 10 degrees below the horizontal. So drawing a diagram of it, here's a packing crate with 50 kg, and what we're doing is we are applying a force going down like this, 10 degrees below the horizontal. So that's like a angle of 10 degrees in depression. This is bad for the packing crate. It's not bad for us. We can still calculate it, but it's bad in terms of real life because we are pushing this crate down onto the ground, which is going to increase its friction. This time we talk about friction, so it's going to make it harder to pull. It'd be much better if we were pulling it up like this. This would reduce the friction. And what we're going to do is we're going to calculate this in the horizontal and the vertical planes. Let's see. We've got 120 newtons on that diagonal force. So let's break this down and have a look at the horizontal and the vertical of it. see if I can scoot this across. Let's look at the horizontal first of all. Horizontal. I don't know if I'm going to look at the horizontal or the vertical. Vertical. So I'll do both of them at the same time. I have to do both of them anyway. So we're going to use some SOHCAHTOA. Let's see if I draw it down here. I might have enough space. Here's my force triangle. We are pushing down or pulling down with 120 newtons on the hypotenuse. We already know that it's 10 degrees. Let's use SOHCAHTOA to find out which one we're going to be using. Here's SOHCAHTOA. Okay. Right. So let's call the vertical bit y and the horizontal bit x. So I want the horizontal first of all. Oh, I'm going to draw a little guy here. So this will be my adjacent here. This will be the opposite. This will be my hypotenuse. We're looking for adjacent. And the adjacent, and I've got the hypotenuse, adjacent, and I've got the hypotenuse, adjacent, and I've got the hypotenuse. That's a CAH. So I'll write that down as cosine of the angle is equal to the adjacent over the hypotenuse. So that's cosine of the angle, which is 10, is equal to the adjacent, which I don't know, over the hypotenuse, which is 120. Multiply the 120 up to the other side, so we get 120 cosine 10. That's equal to my horizontal force, which is effectively the pushing force on this crate. Let's get a calculator and do that. 120 cosine 10. 118.18 looks like newtons. Again, this is the pushing force. We can add it to the diagram if we wanted to, but it's basically saying it's 118 pushing it this way. Okay, great. Now we're going to do the same thing, but we're going to do it, let's do it, this one in blue, and I'll do the vertical in red. We're going to do the same thing for the vertical. The vertical is going to be pushing down on this. We're going to be using the opposite over the hypotenuse, so that will be the SOH. So let's get a SOH. That will be sine of the angle is equal to the opposite over the hypotenuse. As sine of 10, the opposite is going to be y. We just call it y. The hypotenuse is the 120. And then we're going to multiply up the 120. So it looks like this. Sine of 10 is equal to y. It's exactly the same formula, which is really nice. Really easy to remember. Now let's type this in. So 120 sine 10, okay, is 20.83. 20.83. That's meant to be an 8. Let's make it look like one. 833, is it? Nah. 837. 838 if I round it. Newtons. Okay, great. So now we've got this working it down in the vertical direction. And this is pushing it in that way. So I guess I could draw that on here as 20.838. Right. The reason why I say that is because the box is pushing down and we are pushing down, and both these things are going to contribute to the friction. So let's have a look and see if we can calculate friction now. Let me move this off to the side. Okay. So let's get another color for friction. Friction is fun. So it's fric is equal to mu n, right? Which is Fun, which is F is the friction force created. It's going to be resisting our motion. And then mu is the coefficient of friction, and n is the downwards force, the normal force. It's down, or I guess it's the upwards force, the reaction force, downwards force. Let's have a look. Vertical force, we can call it. I want to check what are we doing here. Determine the acceleration. All right. So after we apply the friction is going to be pushing it back. There's still going to be some horizontal force pushing it forwards. Right now we've got 118 pushing it forwards, but this might come out to be like 100, and we were left with 18, which goes towards the acceleration. So there's another step after this as well. We'll get there in a second. Anyway, the friction force is the coefficient, which is 0.2 from the question over here. And then the normal force is going to be the two things combined, because they're both pushing in the same direction. There's the vertical force from the chain, from the thing we're pulling it with, which is going to be 20.838 plus the downwards force from the box, which I didn't calculate. Let's do that real quick. The box, I'll write it down here, is going to be pushing down with gravity times by its mass. It's just F equals ma or F equals mg, because A is the gravity, acceleration is gravity in this case. So we've got 50 kilograms times by 9.81. Let's see how much it's pushing down by. 50 times by 9.81 is equal to 490.5. 490.5 newtons. This is pushing down, this is what the box is pushing down with its own weight. Instead of saying 50 kilograms, we can say it's pushing down with 490.5. Okay, so I better add that onto my friction over here. So that'd be 490.5. This is the friction force. Let's add these up and calculate that all together. It's quite a chunky calculation. We add in the 490.5 plus 20.838. Great. And then we times that by 0.2. So it's 102 newtons. Look at that. I guessed about right when I said about 100. So it's 102.26. Let's round it up to 27. Okay, this is the friction force. This is the resisting our motion force. So my diagram's getting a bit busy now. So let's grab it and drop it over here and see if we can make sense of what's going on. We're pulling this chain and, well, either way, clean my box up quite a lot. We are basically pushing it forwards. We have this pushing force of, we did it earlier, 118, right? 118.8. This is the pushing force going this way. It's 118.18. Let's do it in blue. Now, the resisting force, which is done in pink, is 102. So this is the friction. This is friction pushing it backwards, which is 102.27 newtons. This is all we care about right now. We want to know what is the resultant force of this. We can look at the resultant force, or the net force, in the horizontal. Is going to be the 118.18 minus the 102.27 pushing it back. Let's see, 118.18 minus this is 15.91. 15.9124. This is what's left over of the horizontal force, and this is going to contribute towards acceleration. Remember, in the question they're asking us for determine the acceleration of the case. So now we're going to use F equals ma to calculate the acceleration of the case. We've got this force pushing it forwards, and we know that the crate is 50 kg. So we can use F is equal to ma to calculate its acceleration. We know there's a force pushing it forwards of 15.9124. We know the mass of the crate is 50 kilograms, and then we can calculate the acceleration from this. We just need to divide 15.9 by the 50 to transpose it. So just to be clear, we're doing 15.9124 divided by 50. This will give us the A. Take this number, it's already in my calculator, divide it by 50, and we get 0.31. 0.318248. That's a bit too many numbers, but that's fine. Meters per second squared. This is the acceleration of the crate after all that. Quite a long question, but very common. Very, very common, like pulling a crate, pulling a box, and working out its acceleration. On to the next one. Okay, we're going to do question number 11 here. Let me move this out the way. Alright, so a screw jack is used to support a load. Screw jacks are pretty simple, they're pretty nice, pretty easy to do. Let's draw a quick diagram. A screw jack, I'm sure you know what a screw jack looks like, but I'm going to draw it as a quick diagram, which is basically the amount we're lifting it, and then the effective length of that turning arm. Let's have a look. We've got an effective diameter of 120 mil. They always change that a little bit. Sometimes it's diameter, sometimes it's radius. And what's going to happen is we are effectively pushing this thing around in a circle in order to jack this up by 5 millimeters. We're going to be pushing this around in a circle. That's the path taken. This is important for the movement ratio calculations. Let's write down, let's write this down as the diameter. The diameter of this thing is equal to 120 mil. Let's write down our formulas. We're going to be using EFM. EFM is how I remember it. That's efficiency is force ratio over movement ratio. We've got to be careful because they changed the language a few times. Like force ratio, movement ratio, looks like it's okay this time. But force ratio is the same as, they say it different ways. Movement is the same as velocity. And force, I can't remember, they say it some other way. But anyway, this is my EFM, like a radio station, right? I can remember it this way. My force ratio. And force ratio. There's two numbers, and one of them is big, one of them small, and I know the big number always goes on top, so this will be the force I'm lifting in this case. I'm not using proper language. There's probably another way to do this, like another way to say it, but I'm trying to avoid technical language. I'm trying to remember this in simple, common English, something I can remember for a long time, and that I won't forget, or when we're packing in all that other information for GES1 and GES2, I don't get confused between everything. So this is the force lifted. Really, it's like the applied force or the load I'm lifting, and this will be over the force I'm pushing in. I don't want to say applied for this one because I'm applying this. Yeah, I guess it'll be load over applied. So it's the force lifted over what I'm pushing. Force I apply. Force I apply. Apply. Because I know I'm going to be lifting like 1,000 newtons by applying like 100 newtons, for example. And let's see if I got any of that. The jack, yeah, if the applied effort is 80 newtons, so we're going to have 80 newtons on the base. And then we are lifting 300 kilograms, so we're going to convert that into, well, we can do it over here. We've got 300 kg. We times this by 9.81 to turn it into newtons, because this is the force we're lifting. The force, yeah, it doesn't have to be force lifted is a thing, right? It could be, you could be cracking open a rock or pushing something as well. It could be side to side, it doesn't have to be strictly lifting, but for my memory's sake, I'm going to remember it like that. So 9.81 times by 300 is 2943 newtons. So we are lifting 2943 newtons, and we are applying only 80 newtons. All right. So this number divided by 80, this will give us the force ratio. 36.78, that's really big. 36.78. For such a small load, we're just applying 80 newtons, we're lifting so much more. Okay. 36.7875. I didn't put a decimal place on that. We're lifting 36 times the amount of effort we're putting into this thing, which is really, really good. Okay, next one, this is the force ratio, so then becomes movement ratio after that. Movement ratio. Now this is, I think of this as pushing a wheel around like a slave galleon, where you got to crank a wheel to lift the load, or you got a horse, a workhorse that's having to walk around in a big circle, so just to lift a load a certain amount. So it's the circumference of the circle that will be traced as we walk around it, as we push around it. So the good news about a circumference of a circle is it's pi d, and they already gave me d. It says pi times 120 millimeters. And it's in millimeters, but it doesn't matter. The movement ratio cancels itself out. It's going to be the distance. It has to be big over small, right? So it's the distance I travel, or you could say applied, over the distance I'm lifting. The distance the load travels. Again, it's like flipped from the other one. So again, this is going to be like the applied on top. The applied movement, I don't know, applied force over the load, which is completely backwards, which is why I just remember the big one has to go on top. You want this number to be a big number. Otherwise you are not increasing your ratio, your force. You're putting, you want to be scaling things up or scaling things down. Yeah, you're scaling things up. Okay. So the distance I travel is going to be this 120. It's going to be pi times 120 mil. And then the distance the load travels is that 5 mil pitch. So we can type those in. We've got pi times by 120. And then divide that by 5. Again, the ratio, the millimeters will cancel out because millimeters on top, millimeters on the bottom, they're gone. And we just get 75. 75.39. 8. Okay, now we got the last one, which is efficiency. So efficiency efficiency is the force over movement. Force ratio over movement ratio. So I won't bother writing it all out because it's really quick, really simple. We just type these numbers in. Again, it has to be a small number on top this time over a large number on the bottom. You cannot have efficiency greater than 100%. So I can remember that by getting them the correct way round, because if I calculate this thing, it comes out to be over 100, it's no good. Or over 1, because this is going to be a decimal. It's going to be no good. So let's get a calculator. We do 36.7875 divided by the 75.398. It's 0.4879. 0.4879. I can times by 100 to turn into a percentage. Either one is acceptable. 0.48 means 48%. I'll write it as 48.79% efficient, just to be clear about that, by timing it by 100 in my head. That's it.